Hi everyone, I'm Tsubasa Shoshi, a master's student of the University of Tokyo. Today, I'd like to talk about our research, termination analysis for the pi calculus by reduction to sequential program termination. The pi calculus is a concurrent computation model. There have been studies on termination analysis for the pi calculus. However, most of them have been theoretical. There have been little effort in developing fully automated termination verification methods and tools. As far as we know, Kobayashi's typical is the only tool, but its analysis is quite limited. Now we propose an automated method for proving termination of pi calculus processes. We translate a pi calculus process to a sequential program so that if the sequential program is terminating, then the original process is terminating too. Our approach enables us to reuse powerful tools developed for sequential program termination. We also have implemented a termination analysis tool for the pi calculus based on the proposed method. This is the outline of our presentation. So let's begin with the pi calculus. The pi calculus is a concurrent computation model in which processes are interacting with each other via channels. The syntax of processes is given as follows: in action, output, input, replicating input, parallel composition, creation of a fresh channel, conditional branch, and creation of a non-deterministic integer. For technical convenience, we separate arguments into two parts, integers and channels. Now we prepare variables, integers, and integer operations as simple expressions. Next, we will introduce two main reduction rules. The first reduction rule shows that if there is there are an output and an input on the channel X, the communication between them occur. In the second rule, we replace an input with a replicated input. The replicated input is remaining. So let's see the Fieldbus process as an example of the process. The process in the first and second lines works as a function server that computes the nth Fibonacci number in parallel and returns the result to the channel O. That is, if n is smaller than 2, one is sent to the channel O. Otherwise, channels S1 and S2 are used to transmit the n-1 Fibonacci number and the n-2 Fibonacci number, respectively, and the sum is sent to the channel O. The process in the last line sends a request for computing the nth Fibonacci number, and so note that we omit the trailing zero process. Okay, next I will explain a basic translation from the pi calculus to a sequential language. In our pi calculus, the replication constructor is applied only to input processes. So, non-termination is introduced by only by sending messages to replicated input processes. So in order to verify the termination of processes, our approach checks that there is no infinite chain of communications on replicated input channels by converting such a chain of communications to a chain of function calls in the sequential program. A replicated input is converted to a function definition. On the other hand, a non-replicated input is just ignored and converted to non-deterministic instantiation. We convert an output to a function call and the parallel composition to the non-deterministic choice. So let's revisit the Fibonacci process. You can find that the replicated input is converted to a function definition. The output on the channel field are converted to the function calls, and non-replicated inputs are converted to non-deterministic instantiations. Also, the output on the channel R is just converted to scale because there is no replicated input on the channel R. Yeah. And let's explain the termination of the process follows from that of the sequential program. The Fibonacci process has a chain of communications on the channel here like this. And the translated program has a corresponding chain of function calls like this. So, and now the sequential program is terminating. So that means this chain of function calls has a finite length. Therefore, yes. Therefore, the length of this chain of communications is finite too. So we can conclude that the process is terminating. Next, we will discuss the soundness of the basic translation. We proved that the soundness of the basic translation, that is, the process P is terminating if the translated program SP is terminating. We briefly explained the proof strategy. Basically, our idea is to show that the translated program simulates the process. If we reduce P to P1 in one step, then we can reduce the corresponding program SP to SP1 in some steps. Then we can conclude that if P is non-terminating, then SP is non-terminating too. However, it is not easy to show the simulation relation because there is a slight mismatch between the reduction of a process and that of a program. For instance, look at this process. This process is translated to this program with a definition for function f. In the PyCalculus, both outputs can be used. We can use the output of one after the output of 2 is used. On the other hand, in the sequential program, we must make a choice. So we cannot call f of 1 after f of 2 is called. To fill this gap, we introduce a non-standard reduction for sequential programs, which does not discard branches of non-deterministic choices. The proof strategy is shown here. First, assume P is non-terminating, and then we show that the translated program SP simulates the original process P using the non-standard reduction, which keeps branches of non-deterministic choices. And then this implies that there exists an infinite non-standard reduction sequence of SP. Finally, it remains to show that there exists an infinite subsequence that corresponds to a reduction along a certain choice of non-deterministic choices. This step is a corollary of Konig's lemma. This is because this infinite non-standard reduction sequence can be reformulated as an infinite tree whose branches correspond to non-deterministic choices and whose passes correspond to reduction sequences. We can find infinite paths from Konig's lemma, and this path becomes an infinite standard reduction sequence of SP. Next, we will explain improved translation using refinement types. In fact, the basic translation has a weakness. The basic translation loses information about values received by non-replicated inputs. Look at this out. Look at this process. And the process in the first line works as a function server that receives an integer n at the channel O and sends n-1 to the channel O. And let's see the second line. If n is smaller than 0, 1 is the process ends with outputting 1 to the channel O. Otherwise, for this x, since this x is equal to n-1, so the first argument of f is monotonically decreasing until it becomes negative. So the whole process is terminating even though the process in the third line sends any request to the channel F. By the basic translation, we get this program, and this non-replicated input is converted to this non-deterministic instantiation. So because we do not have information about values of the value of x. So we lose information on x here. This causes this program is non-terminating because there is an infinite loop like this. So our solution is that we recover information about values received by non-replicated inputs using refinement channel types. This channel type describes that channels are used to transmit both integers and x tilde that satisfy a formula phi and channels of types cap tilde. So let's revisit the previous example. This thread has this kind of types. It is because the channel thread is used to transmit an integer n and a channel R, which is used to send n minus 1 that is smaller than n. We can also assign this S. We can also assign this type to the channel S. And next, we will refine the translation relation for inputs. We insert assume statement according to the refinement types. Therefore, the sequential program becomes terminating, so we can verify the termination of the original process. Now, we'll explain a refinement type inference PCC solving and a pitfall, and its pitfall. We can reduce refinement type inference to a problem of CHC solving. First, we prepare these templates based on the simple types. Next, we generate these CHCs from the typing rules. For example, the first constraint comes from this output. So under the condition n satisfies P1, this n minus 1 must satisfy this P2. And also, the second constraint comes from this output, and third constraint comes from this output. And there are various tools for CHC solving, and this is a kind of a solution. This is an example of a solution by a CHC solver. Using this solution, we can find that we can get the terminating program. However, you can find a pitfall in the refinement type inference. A typical CT solver may return a trivial solution which instantiates all predicate variables to true. It is because the head of every CHC is an atomic program on a predicate variable. So using this trivial solution, we gain the non-terminating program. So in order to prevent this kind of group, we add this extra constraint, and a CHC solver may return a solution like this, and we can get a terminating program. Next, I will report the implementation and experiments. We have implemented a termination analysis tool for the pi calculus based on the import method using refinement types. First, we inferred refinement types in our pi calculus. We used Spacer and Hoist as backend CHC solvers. Then, we translate the pi calculus to a C program. Finally, we used Ultimate Automizer as a termination analysis tool for C. And this table shows results of experiments. Test cases consist of two categories. One is taken from typical, and the other is prepared by us. We ran over two and typical on those test cases. For the first category, our, our tool fails in those four test cases. It is because we cannot make reasoning about synchronization over multiple channels. And for the second category, our tool outperforms typical. We can we can show the termination of this process, but typical cannot do so because it is because typical can handle only the standard order on natural numbers as a well-founded relation on termination arguments. Finally, we discuss related work and conclude. Deng and Sangiorgi's type system for termination analysis inspired our work. The key idea is that values of messages monotonically decrease in every chain of communications. Hobbles's typical is a termination analysis tool for the pi calculus. It can only verify termination of processes where natural number arguments monotonically decrease with respect to the standard order. In conclusion, we propose an automated method for reducing termination verification for the pi calculus to that for sequential programs. We also improved the translation using refinement types. We improved the soundness and implemented the tool. Future work includes a further refinement of our redaction and applications to other concurrent languages. So, thank you for listening.